so it's about time to get started, right? So welcome to Applications of Scientific Computing or Computation ES 205. Does that sound about right? Cool. I'm trying this cool new setup, which I figured might be good when we get a little deeper to the math, because this allows me to actually like draw things on the paper. And the best part is that this also allows me to record that. So I'm recording as we speak, and then if it all works, then I will put it online, so you don't really have to take any notes, in theory. And it should just work nicely. Why do I have? Oh, yeah, that's better. Okay, so first, you probably figured out already. So it's a little ridiculous, this setup for these introductory slides, like where is the lecture room and so on. But I just wanted to test the setup already. So as you probably figured out, we are meeting here in this room on Monday, Wednesday, Friday. It's from 2 to 3. And I think it's the usual deal. We are supposed to end like 10 minutes early, right? I was initially surprised. I actually just started here like this January, so I'm relatively new to this business. I will introduce myself in a little bit. So the lectures are here Monday, Wednesday, and Friday, 2 to 3, and the recitations are Thursday, 11 to noon. The first few recitations we will use to introduce Matlab. We will get to that, and we will get to our TAs too. So first, let me introduce myself. So my name is Ladislav Kavan. Here is my email. I sit here in the Levin Hall, and you are welcome to swing by during my office hours, Wednesday 3 to 5 p.m. So as I said, I just started at Penn relatively recently as an assistant professor. So I don't have a ton of experience teaching. I just taught my first course this past semester in the spring. One thing I noticed there was that that was about physics-based animation, which is like really cool topic. But then one of the prerequisites was linear algebra, and I found that like the linear algebra the student had was not really as good as I was hoping for. And this is exactly what this course is supposed to cover. Actually, maybe as it's a relatively small class, maybe we could just go around and say, what is your name, what is your program, and year, real quick. Could we do that? We can skip you. I'll introduce you in a little bit, so you can start.
Sam Merritt, I'm D&D senior.
Senior? Cool. Yeah.
Oh, I'm Maya Epsworth, D&D.
Okay.
I'm Vincent CIS, junior.
I'm Clara, I'm Nats, and junior.
Okay.
I'm Matlab, that's junior.
I'm Spencer. I'm a one senior, so matriculating into Robo-MS.
I'm Jerome. I'm a sophomore in CS.
I'm Sedan. I'm a sophomore in CS.
I'm Justin. I'm a sophomore in CS. I'm Van. I'm a junior in CS.
And then also junior.
It's I still haven't learned completely these years. So wait a second. Juniors? No, freshmen, sophomore, junior, senior, right? Okay. The system is completely different in Europe. That's where I come from. Okay, enough about that. So TAs. That's why I didn't introduce Shawn, because she is one of the TAs for the course. The other one is Jake. He couldn't make it today, unfortunately. These guys will also have office hours, and most importantly, they will be available to help you with your homeworks and projects, ideally during the recitation hours. So let's do some more interesting things. So what the course is going to be about. Applications of scientific computation, that could really mean anything, right? I don't know what you were sort of thinking when you were signing up for it. Some people told me that this is like a Matlab course, which I don't think it's completely true. I will talk about Matlab in a little bit. So I think this course is mostly about linear algebra. Yes, here I could finally start using my annotation, so I can test it out. Maybe I can do the lock. So did you have some linear algebra courses before, some math sort of stuff? Yeah? So this is not just about the math. So the math is sort of like interested in asking questions why, right? Like why this is true. We need to come up with a proof to like show some interesting property of vector spaces or something like that. But here we will be also interested in really in the application. So I could also call this course Applied Linear Algebra, would be also a pretty good name. So applied means that we will be using linear algebra to a wide variety of problems, because linear algebra is really used everywhere in computer science and engineering and computational science, like solving, like the guy who was talking here before about like planes and things like that to analyze statics. I have actually a bunch of examples of just some applications of linear algebra. But again, this is really, really widely applicable. I think like any CS major should have a course like this or equivalent about like basic linear algebra, how to apply that. So my favorite area is graphics. Transformations in lighting. We'll talk, for example, about radiosity. I don't know if you guys heard something about like rendering. So this is the problem when you have like some scene in graphics, like in a movie or in a game, and you have to compute the lighting, the illumination. So you know that there are some light sources, like in this room there are some light sources, right? They are shining light, and that the light like bounces from objects by different laws, right? There is like diffuse reflection, there is specular reflection, and the light bounces all over the place, and eventually creates some illumination, some shading, some lighting. And the basic techniques, they can be expressed in the language of linear algebra. They can lead to a system of linear equations, which you then solve, and you get the result, some nicely lit image. That's not the only application in graphics. That would be like a rendering application. The surface modeling, spline, subdivision, those are like more the geometry related things. So where the geometry comes in, like if you have the characters, like the Navi here, so they are represented typically by some surface, right? And the surface is a geometric concept. And for example, what the splines and subdivision are about, they are about that you have just a fairly coarse representation of the surface. So let's see if this is going to work. So if I'm like an artist, I just want to have like a few control points on some very coarse curve, and then what the splines give me basically is a smooth version of that. For example, something like this. The subdivision is essentially the same idea on two-dimensional surfaces. Here I showed it on a curve. But this also works for 2D surfaces living in 3D, and that's exactly what is used like in feature animation quite a lot. All the Pixar characters, for example, it's a little better visible on like Pixar things. You can imagine your favorite toy character. They are all nice and smooth, right? If you recall the movies, and that's because they are using subdivision surfaces. Okay, maybe we can close the door. There's a bunch of other sub-areas in graphics where linear algebra is used. Like when I was teaching phys-base, it was coming all over again. Like when you are doing fluid simulation, for example, that means discretizing the Navier-Stokes equation. That like starts with like this continuous math. You eventually discretize it, do some like mathy tricks, and guess what? You end up with system of linear equations which you need to solve. And that's exactly what linear algebra, what this course. One of the things this course is about, so that you are able to solve it. So this is really like the starting point for many interesting areas. Another one is robotics. So robotics is interesting because lots of these robotics problems are not strictly linear, but lots of these concepts from linear algebra are still very relevant to them. So like kinematics and dynamics of robots. Do you know these terms? Do you know what is it? Cool. So kinematics is about like computing the global positions and orientations, and dynamics is when the motion is involved. And even if we are dealing with nonlinear problems there, and I will also try to explain you like what these nonlinearities are coming from. then still a linear algebra still applies, because what do you do typically to tackle some nonlinear problem is by constructing local linear approximations, and there is where you can unleash all your linear algebra knowledge for these locally linear things and apply all these things there. It's sort of vague. I'm just trying to give you some high level idea. Actually, we will go through some examples. You will actually do all of these things in your project, so you will get a much better idea. Now I'm just trying to give you an overview. Transform coding, that's something I was really excited about when I was about like your age at this point, like all these JPEG compressions, wavelets. Maybe it's not so cool today, I don't know. I just thought it's really cool that you can just like represent it in some other space or basis formally, and there you can just discard lots of the data without losing much of the signal. So this is exactly what transform coding is about. So we will be talking about bases, or on a high level, it's about representing discrete signal in like different ways to look at it. And the bases used in JPEG, the Fourier basis or the discrete cosine basis, those are some really interesting bases that have the property that if you take some real world signal, like recorded audio, like the audio I'm recording right now, or video, like they take an image, if you project it into the basis, then all of a sudden most of the coefficients will be very small or even zero, so you can discard them. So this is a way to compress signals very nicely. Wavelets are even more advanced type of bases, which have the sparsity and like the local self-similarity and sparsity structure. I don't think it will go too much into wavelets and these special bases, but the point is that like the theory of linear algebra, like the orthogonal bases, that's basically the underpinning of this transform coding. So another thing is linear dynamical systems. That also comes up in robotics, I guess. So this comes to, I think, control theory, that we have some complex dynamical system, could be like a plane or drone or something like that, and we want to figure out how to control it. So for example, in a robot, what would be the control forces in the actuators, control torques, we need to apply so that our structure of a robot does what we want it to do. So you can see that there is like tons and tons of applications. Another one is statistics. That's maybe the thing that's really cool these days. I don't know, you tell me. This goes to like the big data thing, Google, and everything is connected. All the websites are connected, and we have tons and tons of data. Right. So if you, for example, gather all the, if you like put some word like frog and you do Google image search, you will get like gigabytes and gigabytes worth of data. So the statistics is about sort of making sense out of these heaps of data. And most important question is, can we extract some useful information from all these things? So there were like some really cool things I recall seeing in graphics. That's what is my area. Like if you take some famous like building, for example, like the Colosseum in Rome, so chances are that like lots of tourists took pictures of it, right? And put them online. So you can just gather them from Google. You just gather all these pictures. And then you could think, oh, maybe I can reconstruct the entire thing because I have it sampled from all over the place. Millions of people took pictures. So if I take all these pictures together, maybe every single picture, one of them is not so interesting. There is so many of them. But if I take them together and apply some interesting machine learning or statistical thing, then I can like extract the real thing, maybe the 3D model of the Colosseum or something like that. So specific examples, which we will look at because it's very important. Principal component analysis. Have you heard about that? PCA. That's a really useful technique for discovering basically relationships or correlations in data. It's also related to the PageRank algorithm. Have you heard about that one? That's the Google algorithm. I think that will be the last and best project, or maybe not the best, but maybe the most relevant these days. Yeah, this is just to clarify. Some people told me that this is like a Matlab course, so that's not really the point. We will be using Matlab because it's a good tool for linear algebra problems and some other problems. But here it's not the goal. It's not my goal to teach you how to do things in Matlab, even though that might be useful to you too. But here the Matlab is going to be just a tool to solve these problems. So you get hands-on experience. There's like quite a big difference between just knowing all the theory and being able to answer all the questions, like prove that this type of basis is orthonormal, and actually doing it, actually computing, getting your hands dirty with some actual numbers and large matrices. The thing is, the interesting thing about linear algebra is that the algorithms there are quite good at this point. So we have computational teeth to actually chew on and turn these problems. So even with like really large data, and that's where it starts being interesting, being like large images or detailed characters or lots of like documents downloaded from the internet, then Matlab is really good at handling relatively large data. Of course, you need to be careful because computers have their limitations, and that's exactly what you should learn, basically, how to solve for largish linear algebra problems. So there are some specific projects which we'll be doing. I guess it will probably be the most hands-on experience for you, the project. There will also be some homeworks, but the homeworks will be, I guess, more like prove something or do some smaller exercise. The projects will be like almost like small little deliverables in like some bigger like software engineering or something like that. And we will do them in Matlab. So do you have some Matlab experience so far? Yeah, okay, cool, good. So you will learn the basics of Matlab. I guess mostly thanks to my TAs. It's not a big deal. If you know some other programming language like C, C++, or some other like Python or Java, then you will find probably Matlab easier than that. Of course, I should also mention that linear algebra is by no means tied to Matlab. It is like no equation between like solving linear systems and Matlab, right? You can, of course, implement all these algorithms in many other languages. It just happens that Matlab is actually a nice GUI, nice user interface, graphical user interface, or command line interface as well, for the actual solvers that solve the actual linear algebra problems numerically. Okay, so what projects we'll be doing? There's the coordinate transforms for graphics and robotics. So this is basically forward kinematics for robots. So you will have to figure out how the coordinate transformations, and don't worry, we'll be talking about all these, about how coordinate transformations work and how to compose them together to get a motion of some articulated structure. Like robot is an example. Human is actually not such a bad example of articulated structure either, right? Because those are like almost rigid bodies which are connected by some rotational joints. So, analyzing modes of vibration, linear dynamic systems. So I think we will look at like the simplest possible dynamical system, which will be like one-dimensional rope or some sort of spring thing, and we will look at what are the vibrations subject to some excitation of the spring. Splines, those are the curves in graphics. I think I sort of gave you the idea. So splines are like piecewise polynomials which are joined together to create nice smooth curve. It's always nice to see something smooth, right? Like think Pixar characters, smooth means nice. But the Pixar guys say you can have like a lot of error, but as long as it's smooth, nobody's going to notice. So splines are nice smooth curves which you will compute. Guess what it leads to? A system of linear equations, but with some special properties which allow you to solve it quickly. The transform coding, that's what I was already talking about. So this is like what is being used in JPEG, MPEG, all these compression standards. Also for audio, of course. And the PageRank algorithm, that's basically like a mini Google sort of thing. It's like a matrix of documents. It will try to find out which documents are most relevant for a specific query. And I'm not sure there's going to be some PCA. There should be some PCA stuff. I can't remember it right now. We'll definitely talk about that. So, of course, grading. You need to do grades. So the projects are the biggest chunk of it. Then there are the homeworks, and I think we'll do a midterm and final exam. That's, I think, the standard, I suppose. You probably know this better than I do. But if you have any questions, feel free to just ask. Okay, just a few more organizational things. Do you know Canvas yet? So you have been using it for some courses before?
Some classes have started.
Huh?
Some classes use it now.
7 classes?
Some.
Oh, some. Yeah, I was gonna say let's try to use it. I'll try to set up something. I don't know if you got some notification. I think you were all automatically added to this class if you sign up for it. So there's this older system like Word. So the Canvas is like the newer, more flashy system for doing the same. So doing like the standard course organization stuff. So I'll put there the course notes, even though maybe I'll just like do like YouTube videos and put links to, because these are the course notes. I might also post some of the slides and so on. The assignments, that's important. So the assignment description, what you are supposed to do, that you will find on Canvas, that will also be a deadline. And there's a system to collect the assignments, I hope. I haven't really tried it before, so I actually just try to set it up. So there is like a first like proxy homework, which I created like a test assignment just to test the system out if it's all working. So I would like you to submit there like a hello assignment text file just with your name or something. It's for 0 points. It's really just to test the submission system if it's working then for real assignments. I think it should be working. It's good to try. Okay. So that's Canvas. Try to do this, please. The thing for discussion, which I really liked the last semester, is Piazza. Again, probably know this, right, from other classes. Yeah, so I guess we will use that too. The point is that emails are old school, not really working that well. We don't have a large class, but still. It's better to use a discussion forum than just send emails to people, especially because you might get your answers faster, or somebody might have asked the same question before. Here is the link. I think shouldn't be that difficult to find. There might be also some integration between Canvas and Piazza. I haven't totally figured it out. I don't think we need to care so much about that. Or does someone know? Yeah. So my understanding is that Canvas is like for administering the course, like having the course notes there, assignments, homeworks, and Piazza is for like basically discussions. If I have some question, something's not working in the homework, there is some problem with the assignment, this is the place to ask a question. Or something wasn't clear in the lecture. Oh yeah, here is the standard boilerplate. Be nice. I guess let's clarify what does it mean to do things individually. So it's totally fine to talk about the problems. If you are like struggling with something in the homework, it's totally fine to talk among each other. It's even better to ask questions on Piazza or talk to TAs or myself. What is not okay is like download something from the internet and then change the variables and then submit that, or take something from your colleague and do some trivial modifications to the code, or even non-trivial modifications to the code and submit that. That's not okay. Yeah, I think that's the standard thing. The point is that this is about applied linear algebra, so you will really get the most of it by applying it yourselves, getting your hands dirty with some actual numbers and problems to solve. So if you are not doing that, then we are just wasting time. Here's a textbook, which is really good textbook. Gilbert Strang is professor at MIT, and he has actually also lots of online lectures on linear algebra. I was actually looking at some of them, and they are really good. They are sort of superficial sometimes, just like 2x2 example, and But like to convey the basic ideas, it's absolutely terrific. So I wholeheartedly recommend the textbook. Might even refer to it for some homeworks, or I haven't totally decided yet. It's definitely a good thing to get. You might be able to get it from the library, I think. If you are really into Matlab and you want to be like the Matlab hackers to find out all the cool things it can do, then you can get like a book on Matlab. I probably wouldn't bother so much unless you are really into it, because there's like lots of online help for that too. I never really used any of these books myself. But if you want to do it, or if you will be using Matlab for then some other courses or some independent studies or things like that, go for it. So Matlab, what is that about? So Matlab stands for Matrix Laboratory. So this is what this course is mostly about. It's like sort of operating with matrices. We'll soon find out that like linear algebra revolves a lot about vectors and matrices. And Matlab is really good at dealing with matrices numerically. Numerically, that means that there actually is not exactly one-to-one correspondence to the mathematical world, right? In the computer, there is no such notion like a real number. You probably heard this before, right? Actually, yeah, I'll find out soon, like where you are at. So the computer does not have anything like capability to store a real number. It only can work with a subset of rational numbers, right? Because it has a finite memory. Typically, the floating point numbers have 4 or 8 bytes. So then it's only that many numbers you can fit in there. So it means that like some really, really small number or really, really huge number, you probably will not be able to represent very accurately. And there's lots of implications, and we'll talk about it in more detail. This is just to explain what I meant by numerical experiments. Okay. So where do you want to get Matlab? So you are sort of in luck. I just got some emails recently that there is like an initiative to get you guys Matlab for free, at least for this year. So all students who are like enrolled in a Matlab relevant course like this one, you should be able to get a free annual license. So unfortunately, the process hasn't been totally finalized yet. It's just like this promise I have from the CETS people. So I was told to tell you, don't go buy it from the bookstore. You could. I don't think it's even that expensive, but it's pointless because you will get an annual license for free. I think at least that's the promise. And of course, there is Matlab installed in the lab computers, so you are also always welcome to use it there for free. Okay, I think, yeah, and the recitation, I hope we can start tomorrow already, the 11 to 12 at 3:09, just over there. Sort of disappointed. I was hoping that there would be some computers for you to play with, but I guess it will be just this style that I guess Shao will show you. Unfortunately, I cannot even make it on Thursdays because it conflicts with our graphics reading group, but Shao is probably maybe even better in Matlab than I am, so she will show you the basic tricks of the trade, how to get it started, how to like get a vector and matrix, some of these things. It's sort of fun. If you could get a Matlab already or on a laptop, that would be cool, but probably might not be possible. Yeah?
You can do like remote desktop, like there's like a remote Windows lab, and you can just like remotely do it. So you can do it actually early. It's kind of slow, but
Mm-hmm. So you can do it from your laptop, is that what you're saying? Oh, that's cool. Oh, that's nice. I didn't know that. Cool. Okay. So I think that's it for the organizational matters. So we can do some real or introductory course stuff, unless you have some more questions on this. This was a very good comment. Any more of those, please? All right. So this is, I guess, still a little bit philosophical, but it's cool actually. So the nice thing about linear algebra is that you can think about it two ways. There is like this, I don't want to say dichotomy, it's more like duality, that you can look at it either algebraically or geometrically. And you can look at the same things from like these two points of view. So like when we'll be talking about vector spaces, then they have like hard algebraic properties, and you can think about it just in terms of algebras. And you may like never give it any geometric interpretation. Like I was shocked when I was taking linear algebra classes when I was about your age. So we had like a professor who was like a really smart guy, and he told us when he was lecturing about a determinant that he didn't know this as a geometric interpretation for like many years until someone told it. So you can be looking at it purely as like algebraic objects, and you can learn a lot about it by doing that. Algebra basically means that you have done it, right? That even at high school, like it's just manipulating expressions. Here I'm talking more about like abstract algebra, so there are letters instead of numbers. The other way you can be looking at all these things, so you can either look at the vectors and scalars and matrices, algebraic objects that have some properties like commutativity sometimes, distributivity, we'll talk about all of these. The other way you can look at it as geometric quantities. So you can always imagine a vector like a little arrow having some geometric meaning. And geometric meaning that you can start reasoning about angles and distances. And you can like draw little arrows and get some geometric intuition. Geometric intuition like 2D and 3D is something that you can imagine basically. That's like what like architects do or 3D modelers. So let's try to illustrate this and with a little more concrete example. So these are coordinates of points in a plane. This was invented, I think, in the 17th century, super old thing by a guy called Descartes. So this is called Cartesian coordinates. It's the super simple concept that if I have like a point or vector. By the way, there is like a subtle difference between points and vectors. So I guess for now I'm talking just intuitively, so don't really quote me on any of these things because we haven't really defined these things properly. But here I just want to say intuitively that if I have like a 2D plane right here and I have some point right here and this is my point 0, 0, then I can say that this point is also represented by some vector v, and then the vector has coordinates 2 and 1. So there is like a tuple of numbers 2 and 1 which represent this vector. So the point here is that the vector I can be looking at as geometrically, right? So it will have some length, this vector. What will be the length of the vector? Square root of 5, yeah, exactly. And there is also important thing, the frame of reference. In vector spaces, we always have this 0, 0 element with respect to what everything is expressed. Everything revolves around this 0 point. So let's talk a little bit more intuitively about vectors. So as I said, you can either think about it as like a tuple of numbers. So in 2D, it would be like a pair, right? Like here, 2, 1. Or you can think about it like an arrow in the plane. That would be like the geometric point of view. Oh, I think I forgot to have light in this camera. Huh. Let's see if that makes it better. So one important thing to notice here is that by default, we are writing the vectors as column vectors. So in a column, we could also write them in a row. And there are real reasons why we want to think about it one way or another. The algebra doesn't care. In algebra, there is no such thing like differentiating between row and column vectors, at least on some level. So this R2, have you seen this notation before? This is how we will denote the set of two-dimensional vectors. So by saying that V is in R2 means that V is by default a column vector. So it's a tuple of numbers, tuple of two real numbers. in theory, vectors could be also not over real spaces, but could be also over different fields. So here the R refers to real numbers. What other vectors could we have if not reals? Slightly tricky question.
Is there such a thing as like imaginary vectors?
Like complex vectors, yeah. We could have like C2 vector, which would be like vector that would be form of 4 numbers essentially, or two complex numbers. So we will not be dealing with those here mostly. Maybe eventually, like the complex numbers come up. The complex numbers sort of like come up naturally, because we have the problem that there is square root of -1. What are we going to do with it? Complex numbers, right?
Would quaternions fall under that category?
Exactly. So if I could have like real numbers, that's where it all starts. Then you can go to complex numbers. Those are like pairs of scalars. Then you can go to quaternions, which are 4 tuples of things. Then the algebra gets like really interesting, and you can go even higher. 2 ways you can go higher, but I don't want to confuse you at lecture number 1. There will be a lot of room for confusion later on. Yeah, this is something I'm quite interested in, all these algebras, especially because these things also have geometric meaning. It's very cool that all these, so complex numbers, they are very closely related to 2-dimensional rotations in a plane. We will, I think, see that. And quaternions, guess what? They are very closely related to rotations in 3D space. Yep, that's a good question. So mostly we will be working with real vectors. That's what really is most of the applications for us will be concerned with. So this might be a little boring. I guess what can we do with vectors? Well, we have to say that, right? So there are two basic things we can do with a vector. You can multiply with a scalar. This sounds like a high school class. I don't know. Is it super boring this for you, or?
I think it's a nice review.
Okay. Yeah, you can multiply by a scalar, or you can add the vectors together. But you can be thinking, how about multiplication? Multiplication of vectors is actually much trickier business. Vectors normally don't multiply, unlike real numbers. So scalar multiplication just means multiply every single one of them. And addition, again, means per component, right? So add these 2 together, add these 2 together, that's the result. So one vector plus another vector gives me another vector. I guess I could also write like the type of these functions. So scalar multiplication could be like a function from R to R2, which gives me an R2 vector, right? And this is like an operation from R2 to R2, which gives me another R2 thing. Is it visible? So this is some sort of operation which has some properties, lots of important properties, which we'll go through in more detail later on, where we'll give it like a little more formal framework. I will not go too crazy with the mathematics, but it's good to understand what properties these things have. So this is the algebraic way you can look at the operations of vectors, right? This is some functions, some operations with some algebraic properties. The other way you can look at it is, again, through the geometric interpretation. And obviously multiplication by a scalar value, what does it mean? Well, that means if I look at my vector as an arrow, that means just making the arrow longer, right? If I have a vector of length square root of 5 and I multiply by scalar 2, then I will have like vector of length 2 square roots of 5, right? Now the adding vectors is a little more funny. You can draw a diagram like this, right? So let's see. So I had a vector v. So the vector v had some coordinates, right? Some vx coordinate and the y coordinate. So v was vx, vy, and I added it to vector w. So here is one thing about vectors that you should always keep in mind. The vectors normally should always start in 0, right? But I can sort of imagine that where it started doesn't matter. That what really matters is only like the direction and length of the arrow. So they're like free vectors that I can conceptually move them around. I guess it will be more clear when we get to the exact definitions. But let's see. So if I had another coordinate system, so my vector W would be again something that has coordinates wx and wi. And if I add it together, the w plus v, it's gonna have coordinates, of course, vx plus wx and vi plus wi, right? And it just so happens that geometrically I can draw it like this. I can first draw the one arrow and the other arrow going from there. So this means adding the vx plus this wx here. So this is the wx. I add them together and I get the first component of the vector, which is the sum of them. The same way it works for the other component. And guess what? The same way it would work for any number of components. This is something I was also, like, when I was younger, quite excited about, because like 2D and 3D spaces, you can sort of think about them, right? 2D space is like my whiteboard or this, and 3D space is sort of like the space we live in. But like 4-dimensional, 5-dimensional spaces, it's harder to imagine, right? Like, how do you think about 4-dimensional space? Well, with linear algebra, we have no problem, right? Just 4 tuples of numbers. So that's what we can do. Linear algebra really doesn't care so much about the dimension. You can have vectors of pretty much arbitrary dimension. And with Matlab, you can compute with crazy high-dimensional vectors and matrices. If you have like sparse matrices, you can easily do like 100,000 times 100,000 matrix. You can be doing with like 100,000 dimensions. So I think this is just restating what I said before, that those are elements. These are, reminds us that those are real vectors. So it's a vector space over real numbers. You could also have complex numbers or even quaternions or whatever. Most of the time we'll be dealing with real vectors. So instead of the 2, I can put there n. And that means that I have n dimensions. So here, again, I haven't defined dimension rigorously. There is a rigorous definition of dimension. But for now, you can just assume that that's the number of elements in the vector. So this will be a 2-dimensional vector. This would be an example of a 3-dimensional vector. This would be a 6-dimensional vector. Pretty simple, I guess. Here is one basic operation we can do with vectors, and that's the inner product. And again, we are now talking relatively informally, so but let's see how we can get basically just intuitive understanding of these concepts. So what is the inner product? I guess the inner product, if I wanted to write like a type, I sort of like to think about like the types of things. Like if you have like a programming language, you probably know that if you are specifying a function, you have to specify the types of the arguments and the type of the result, right? So I can also write it in the mathematical notation. So I would have Rn, and it gives me a single scalar. So it's something that takes 2 vectors and returns a scalar. That's inner product. And how does it compute that scalar? Well, it looks at the individual components. So if it's 2D, it just does v1 w1 plus v2 w2. So if I have these 2 vectors, v with components v1, v2, and w with w1, w2. So what I do, I just take this one, multiply it with this one, and add it to this guy, multiply it with this guy. Most have seen inner product before, I suppose. It's also called the dot product or the scalar product. So here are some simple examples. So if I want to compute a dot product of 1, 2, and 3, 4, so I go like this. I compute 1 times 3 plus 2 times 4, right? So that's 11. That really feels like high school. Sorry about that. And here is another example. Gets a little more interesting if you go beyond 2D. So the same definition applies to n dimensions and works really the same way. I just sum over all the coordinates. That's like a pretty standard theme in linear algebra. You like iterate over all the coordinates and something happens there. So this is the simple thing you can do. You just multiply all of these things together, v1 with w1, v2 with w2, and so on, and sum the results. The result is always a single scalar, in this case a real number. If you had complex vectors, the result would be a complex number. But yeah, so if I have an example of two 3D vectors and I will compute their dot product, I just do 1 times 3 plus 2 times 4 plus 5 times minus 1. And here is my result. So the next I have some properties of the inner product I wanted to talk about. I guess let's do this one. So I already sort of broached the concept of length of vector, right? Like the more linear algebraic word would be the Euclidean norm. But really, it's you can think about it just the length of the vector. That's what it means. So how do we compute the length, right? You knew that for the triangle. So we take, if we have a vector components x and y, we take x squared and y squared, and then we take a square root. Right? Now what we can notice that the x squared and y squared is actually the dot product of the vector with itself, right? That's what this v dot v means. That's a special case of inner product when I just inner product the vector with itself. And I just get, of course, the first component squared plus the second component squared. And what it is the square length of the vector. So that means if I take the square root out of it, I get exactly the length of the vector. And this is also called the Euclidean norm. So here is an example of that. So if I have a vector which has components, so you have v, that's x and y, and it's a vector from R2, then its length is going to be the square root of x squared plus y squared. Now, there are lots of properties about the inner product. So now we have defined the inner product. We can be asking ourselves what properties does it have. For example, it has this important property called commutativity, which means it doesn't matter if you do v.w or w.v. Doesn't matter which way you go. So why is that? That's trivial, right? Because the multiplication in reals is commutative. So I can just flip it here and I just get the opposite inner product. That was like a 15-second proof. Everybody understands the concept of like a proof, or basically just justifying why this is true. In math, you would have like a lemma thing or theorem, and then you would have like a proof, which would be basically this, and then it would typically end with like a little square. So we are not being super rigorous about the proofs here, but it's more about actually understanding why these things are true. Right? If just somebody tells you that the inner product is commutative, you should be asking, why is that? What does it follow from? What do I need to assume? And if you think about it, that's actually very simple. That's what it is, right? Okay, so there are a bunch of additional inner product properties and some more cool statements, lemmas, like the Cauchy-Schwarz inequality, but that we will have to do next time on Friday, unless you guys have some questions. Yeah?
Just a quick question. Are these slides / recording going to be available on Canvas?
They will be, yeah, either on Canvas or on the website. I will post them somewhere. I will see how the recordings work out. Okay. Thanks.